Hello everybody, welcome to Blue Marble Science. A couple of weeks ago I did a video on LIGO and I looked at the Livingston, Louisiana facility and compared the elevation data for the pad that the vacuum tubes sit on, and it clearly shows the curvature of the earth. Well, FE Dogma has taken the Hanford, Washington information and done the same sort of analysis, and it shows exactly the same thing. Now, just to remind you what we saw previously, if we look at the west arm for Livingston, we find that the measured elevations above mean sea level at both ends of that vacuum tube are about 64 feet, just slightly more than 64 feet. But the elevation in the center is 63 feet. Now, if mean sea level is truly a flat plane, there's a problem. Those elevations do not form a straight line. They form an arc that looks like that. On the other hand, when we take those elevations and apply them to an arc that has a radius of 3,959 miles, it does form a straight line. Let's take a look at FE Dogma's video. There'll be a link to it in the description.
This is a photo of the Hanford LIGO Observatory in Washington State. It is an interferometer, and each arm has a beam tube that is almost 2.5 miles in length. Now, the light that enters these beam tube actually reflects between two mirrors at each end about 300 times. Now, it is the alignment of those mirrors that is most critical, and what they did is they actually hung them from a 4-segmented pendulum to help isolate them from outside vibrations. And one of the flat earth arguments is that this system would only work on a flat earth because the pendulum would be like a plumb bob, and this would be the only way that the face of both of those mirrors would be perfectly parallel to each other. Of course, a calculation for the globe earth shows that those pendulums would only be out of parallel by 36 1/1000ths of a degree. I think we have the technology to accurately calibrate those mirrors to the correct angle. Also, they actually have to actively monitor those mirrors during use, and they do this with 5 sensor actuators, and that keeps the mirrors within an angular orientation of 10 to the -8 radians. The beam tubes are the other key component. They are 1.2 meters or almost 4 feet in diameter, and they need to be straight enough so they don't interfere with the laser light. Now, here's a very good article explaining exactly how they did the alignment using GPS surveying, and I'll leave a link to this in the description. On page 2 is table 1, which are the allowable tolerances for the beam tube, and this includes the manufacturing process. But if you look here, this is the tolerance from a perfectly straight line that was allowed when they did the final assembly and alignment with GPS, and that was 1.8 centimeters or less than 3/4 of an inch. Now, actually at Hanford down here on page 9, they got it to within 1/2 of a centimeter, which is less than 3/16 of an inch. Now, I worked in commercial construction on large projects, and that is impressive. Now, here's a cross-section of the beam tube enclosure, and the closure is a shell made out of concrete. It sits on a concrete slab, and you can see that the beam tube is off-centered. Now, after the concrete slab was poured, they used this GPS unit on a cart to mark the center line for the location of the beam tube. Now, the beam tubes were manufactured in 20-meter lengths, and they would move the GPS unit 20 meters at a time to get an accurate center line position for the beam tubes. Of course, the critical alignment was during the assembly of the beam tubes, and in the photo right here, you can see one of the brackets that is at one of the beam joints. So what they did is they actually put a GPS unit on top of the beam tube, and then they used these adjustment nuts right here. There's 2 more on the other side until the beam tube was in the proper position. And the other key component is the concrete slab. Now there are blueprints for these projects that are available to the public, and they show the elevations for the top of this concrete slab. So this is going to allow us to understand whether this project was built on a flat earth or on a globe. I'll leave a link to this website in the description, and I'm going to go to the Hanford Observatory and click on the civil prints. This will give you an index of blueprints, and we're going to start with this one, the drawing matrix. Down in the lower right corner is the number of the drawing you're looking at, and this drawing shows the whole facility, and we're going to take a look at the northwest arm. Now the drawing numbers I have circled in red over here match these drawing numbers in the index. Here is the Hanford LIGO Observatory on Google Earth showing both the northwest arm and the southwest arm. And I've aligned the matrix drawing so it matches Google Earth. Now I've turned everything so the northwest arm goes horizontally across the top, and here is that matrix drawing. I have the corner station, mid station, and end stations lined up. And what I want to do is start by looking at this blueprint here, which is this segment of the arm. Now down here where it says location confirms that we're looking at the correct drawing, and this lower drawing is the overhead of the beam tube, but I want to take a look at this profile of the concrete slab up above. These dotted lines up here show the side profile of the concrete slab. Along the bottom, we have distances that are marked off in 100-foot segments, so this drawing goes from 0 feet to 1,400 feet. Over on the left, we have elevations that are 10 feet apart, so each one of these smaller lines represents 1 foot. And at every 100 feet, we have an elevation for the top of concrete slab. So I'm going to start with this elevation at 0 feet that is at the vertex of both arms. This is a blow up, and we have an elevation of 533.78 feet. And I'm adding that elevation to the corner station on Google Earth. And next I want to find the elevation for these 4 distances. Those elevations are on these drawings. Here are the elevations. Now we can see that the elevation decreases by 4.15 feet from the corner station out to the end station. So let's compare this to the flat earth and the globe models. Now on both models, a horizontal line is perpendicular to a vertical line at the location of a surveying instrument, and on both models, a level line is a line of equal elevation above mean sea level. Now I've added water levels to help explain this, but on a flat earth, a horizontal line and a level line would be one and the same, and of course on a globe, a level line would curve down from the horizontal line. Let's start with the flat earth. Now it would make the most sense if we had the same elevation for the length of the arm, because one of the flat earth arguments is that the mirrors on the pendulums need to be parallel to each other and perpendicular to the beam tube. Of course, this is not even close to the actual elevations. It starts at about 3 inches right here, and at the end station it is actually over 4 feet higher. Of course, it would be possible to build this on a slope, and these would be the required elevations using the same rise over run ratio. But that does not match the actual elevations. In the center here, we're just a little bit over a foot lower, and on each side, we're just a little bit over 9 inches lower. And ironically, those elevations represent a line curving up, which of course brings us to the globe. And on a globe, a level line of equal elevation will curve down from the horizontal line. So this is a globe level line of 529.63 feet. And this is a horizontal line that is tangent to the end station. Now what I drew down here is just a smaller representation of this graphic up here showing curvature drop calculations. So here I've added the actual elevations of that concrete slab. And what I'm going to do is I'm going to do earth curvature calculations for each one of these distances. I'll add that value to the 529.63 foot elevation and see if it matches the actual elevations. So let's start with this elevation here. It is 3,200 feet from the end station, which is 0.606 miles. I'm using the Metabunk curvature calculator, and that gives us a geometric drop of 0.24 feet. I add that to 529.63 feet, and that gives me a total of 529.87 feet. That is off by only 0.01 feet, which is less than 1/8 of an inch. At the mid station, we have a geometric drop of 1.01 feet. That gives us a total of 530.64 feet, and that is off by 0.02 feet, which is less than 1/4 inch. At this distance, the geometric drop is 2.3 feet, giving a total elevation of 531.93 feet. And again, this is off by less than 1/4 inch. And finally, at the corner station, we have a geometric drop of 4.1 feet, giving a total elevation of 533.73 feet. Now this is the largest difference at 0.05 feet, but that is less than 5/8 of an inch. Now, as I said, I used to work in commercial construction. I was responsible for a lot of concrete pours, and 1/4 inch over 10 feet is an acceptable tolerance. These numbers are very impressive over this distance. 5/8 of an inch is not even going to be an issue because look at all the clearance you have between the bottom of that beam tube and the concrete slab. And what is very obvious is that these elevations do not work on a flat earth. It would not even work on a flat earth if that slab was designed as a slope because it would be just over 1 foot low in the center. So my calculations support what was said on page 3 of the alignment document. The fundamental coordinate system for the alignment was the Earth ellipsoidal model WGS-84. Now I also use these blueprints to do calculations for the southwest arm. These are the elevations from the vertex at the corner station all the way out to the end station. Again, I have a horizontal line that is tangent to a level line. The only difference is the elevation here is 533.78 feet. And these are the actual elevations of that concrete slab. So for the first distance, we have a geometric drop of 0.26 feet, giving us a total of 534.04 feet, for a difference of less than 1/8 of an inch. At the mid station, we have a geometric drop of 1.04 feet for a total of 534.82 feet. Well, just like the northwest arm, the error is less than 1/4 inch. Next, we have a geometric drop of 2.34 feet for a total of 536.12 feet. Again, just like the northwest arm, an error of less than 1/4 inch. And the geometric drop at the end station is 4.1 feet for a total of 537.88 feet. So here the difference was less than 1/2 of an inch, which is a little bit better than the northwest arm for that distance. Now the maximum deviation for 4 different locations on both arms is less than 5/8 of an inch. And it could be that these GPS elevations are actually more accurate than my curvature calculations. But in any case, 5/8 of an inch is not going to be an issue for the alignment of that beam tube. So I think it's safe to say that the top of slab elevations for those beam tube arms is more evidence of a globe.
Well, there you have it. 2 LIGO sites, 4 vacuum arms, all showing exactly the same thing. A link to F.E. Dogma's video will be in the description. Drop by and see him, subscribe to his channel, and give him a like if you don't mind. He does good work. Now I find this rather amusing because it was Flat Earth that had the bright idea to use these ultra-straight LIGO tubes as a way to prove the Earth is flat. But it's just not working out for them, is it? And now all of a sudden, they don't even want to talk about this. Oh well, better luck next time, guys. Hope you enjoyed it. And remember, the next time somebody says, show me 8 inches per mile squared, just show them a picture of that thing. Hey, don't forget to hit the like and subscribe buttons. Shout out to the patrons and PayPals. And I'll catch you guys on the next one.